Okay, we're in the last unit. This is the temporary structures part of the course, which is, in your words, form design. So what I thought I'd do is get you oriented so that we can get through the two types. We'll be dealing with formwork associated with slabs, and then formwork associated with wall forms, and then with wall forms we also have battered struts. So to get us oriented, you need to get the formulas figured out, and then where do you get the data from these to solve these formulas. So just like everything we've ever done, these are temporary structures, so they've got a couple nuances that you're not used to. But basically, we've got to do exactly the same thing we've always done. Make sure they don't break under bending. Make sure the deflection criteria associated with the drawings is met, and make sure there is no problems with shear. So I'm going to first give you the equations for each of these. These are in forms of the length of the span of the material. So when we put this material together, we're going to have wall forms, we're going to have slab forms. If you're familiar at all with residential construction, these are going to be pretty familiar terms with you. So for instance, a slab form has sheathing, it has joists, it has stringers, and it has posts. If you look at a residential floor of a house, we have sheathing, we have joists, we have beams going down the middle of the house or in certain places, and then we have posts. So the terms are going to be pretty familiar with you. So let's look at, first of all, developing the equations, looking at the variables in the equations, and then I've got three tables right here that are used to populate that. Also, we have a couple citations in your handouts in chapter 4 and 5 handout that allow you to figure out the loading. So, first equation, bending is pretty universal. Little L equals 10.95 square root of FSW. Okay, F is stress. So if I look at the table and I'm looking at F, this is F right here. It's table 4-2 on page 4-5. Okay? So F is bending stress. That's that column right there. Okay, the S is section modulus. That's one of these two columns, and we'll tell you why there's two of them. And W is the loading, and we'll get to that in a minute. So there's one equation. Deflection is going to have one of three constraints. It's going to be based on how much it can deflect. So the three equations in your book are if the deflection is L over 360, if it's 1/16 of an inch across the span, or if it's 1/8 of an inch across the span. So there's three equations. Each one has its own variables. The variables in it are the same. The radical and the prefix number are different. So this is 1.69. And if you look in chapter 6 and look at the format of it, if you follow along in chapter 6 a little bit, you'll see all of these formulas. Okay? It's a cube root. E, minus elasticity, right there. Okay? So the minus elasticity is given. If you look at it's got it for regular wood and plywood, so it covers everything. The I, here or here, depending on whether it's wood or plywood. Okay? The W is the same as before. L, everything stays the same except the radical. Okay, this is 3.84. The fourth root. And the last one is 3.23, the fourth root. Okay, notice every one of those has a little L. The little L represents the length of the span between the members based on inches. So anything that has a little L has inches attached to it. Okay, shear, we have 3 of them. We have rolling. Rolling shear. Okay, that's meant for plywood. We have a shear equation for dimensional. And we have a shear equation for lumber. I'm going to put it like this. 1 by and dimensional. The 1 by is classified as boards, okay? So you have 1 by, it's 3/4 by something actual, but that's for boards. This is for, so these two would be sheathing, okay? That'd be the sheathing, these two guys. And these would be the framing. Okay, rolling. If you look at rolling, it's got big L. Big L is feet. Little L is inches. Big L is feet. H times IB over Q over 0.6 W. So that's the rolling shear equation. IB over Q, right here. That's in the plywood table. Okay, the next one is the boards. It's big L equals H times BH over 0.9 W. H in all of these, this one, and the next one is going to come from this column right here. Shear stress. This is the H column. Okay? And the last one for dimensional is a little bit different. It's big L equals H BH 0.9 W plus 2H over 12. Okay, so you got 3 equations for shear, you've got 3 equations for deflection, you've got 1 equation for bending. Okay, the E we already said came from here, so that takes care of this guy. So it is E here. It says modulus of elasticity. Modulus of elasticity. So there's your E. So you can see out of these guys, this, 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 all come from table 4.2. Okay, and I'm going to color code these so you can see them. If you look at what's left, this, that comes all the way down. These two, actually those two don't. I'm going to wait on these two for a second, if you'll let me. The H comes from green, so I'm going to put H in green right here. F is in red, E is in red, H, We might as well leave that red too, and I'll make green the other table. So let's go H here. So the red letters are right there. The green letters, I, S, IB over Q, I, S. Come out of tables 4.1 and 4.3. So that leaves me only one thing left. That leaves me the W. Okay, unfortunately the W is a wandering value. I'm going to take and kind of manicure these a little bit. So if you got, we're going to go through each table one by one. But if you look at what I've done here, I don't need this column or this column in table 4.1. You can get rid of them. Table 4.2, I don't need this column or this column. We're not going to use those. Okay? We may jump back a little bit, but I doubt it. I don't think we're going to have time or the desire. And then if you look at this, okay, table 4.3, if you can get to it. You've got two great big wide columns. One of the columns says 12-inch width parallel to span. That means it's perpendicular to the members. That's the way we run our wood. We run the main strength perpendicular to the members. So I've got written on it, this is perpendicular to members. That's the one we want. You can get rid of that, and you can get rid of that. So those two guys are gone. So you won't need those at all in this course. So if you want to go ahead and manicure it a little bit, get rid of that, get rid of that. That's going to leave you a much smaller table. We won't be using this either. The layers, if you look at that though, I'd like you to realize that the layers are always odd. That is so, plies means we're taking thin layers of wood and putting them together with phenolic resin or glue. In order for the grain to be going the same way on the front and the back of the plywood, you have to have an odd number of layers. So if you didn't, you'd have one going vertical and one going horizontal if it was an even number. So that's why they're odd, but we're not going to be using that. So why don't we go through the tables and then we'll figure out how to figure that W out. And then I think we've got ourselves in a pretty good position. So if you look at table 4.1, 4.1 has all of your physical properties as far as moment of inertia, area, physical size. Okay. The only thing you really need to know is you need to know that, and I put it in black on your copy, the B and the H are, first is B, which is the width, H is the height. So if you look at our cross section, we're going to have wood, which is rectangular. And when we got the wood, you got to have a width and a height. And the width and the height are B and H. Okay, we'll be dealing mostly in that 2x range. So don't go 4x2. A 4x2 means this. This is a 4x2. A 2x4 is this. Okay, so the B is always first. So if you go into the table then, just find out the member. If you go across, we're not going to need that part of this, so I'll get rid of it. You do need this. That tells you the size. You do need the actual size. The actual size is different than the nominal size, so you need that. It's like a 2x4 is 1.5 inches by 3.5. When you fill in over here, the B and the H, it's not what you think it is, it's what it really is, okay? A 2x4, you wouldn't put 2x4 into this equation. You would put 1.5 inches by 3.5. Okay, so that takes care of that. Then I went and I kind of pared this down. We're not going to be using rough. So the rough column and everything can go. We're going to use the S4S. Surface plane 4 sides, smooth 4 sides. It's the kind you buy at Home Depot and Lowe's, okay? So we're going to be just using those so you can get rid of those rough columns. There's the area in square inches, the moment of inertia, the section modulus, and then when you get to the end, we do not need the number of board feet, but we don't need the weight. So that's going to give you the ability to get I, S, and A for dimensional and boards. So this is going to be for boards and dimensional. Okay, 4.3 is for plywood. This is for plywood. The first column we need, that's the thickness, okay? So you're going to have 1/4 inch, 1/2 inch, 3/8 inch, 5/8 inch, and so on. We don't need the number of layers, okay? That's the plies. If you buy plywood, it'll tell you how many plies there are in the board. The more plies, of course, the stronger it's going to be. Not necessarily the thicker, but the stronger. So I can buy 1/2 inch plywood with 3 ply and 5 ply. The 5 ply is going to be stronger than the 3 ply. Okay, the effective thickness, we don't need that one. So I didn't even put it down there. So effective thickness, get rid of that one. That moves us into area, and now see the 2 big columns that have 1, 2, 3, 4 entries, 4 columns, sub-columns in it. The second big entry, we don't need that at all. Okay? I wrote perpendicular to stud. That means it's going perpendicular to the members. That's what we want. So you can get rid of that whole big second, and you can get rid of the weight. Both columns. The weight of a sheet and the weight per square foot. So that leaves us this little area right here. So in there, we do need all of those. We need the area. We need the moment of inertia. We need the section modulus. And we need the rolling shear constant. So this will be used for plywood. This table will be used for dimensional and boards. And that fills in everything over there that is in green. Everything I've got circled in green. Okay? This, except these BHs, the BH comes from this right here. Okay? Okay, that leaves us with the stresses now. So if you go back to table 4.2, and you look at that, it's got representative working stress values for lumber at 19% moisture content, continuing a prolonged reuse. Okay,